Okay. Say we have a multi-variable function. Okay. So it will be looking like f is equal to f y is equal to f of x1, x2, so on up to xn. So this function depends on n variables. That are independent. What are those n variables? x1, x2, xn. Okay. Now, if this is the case, this function should have some. Say this is the function space. Fine. In this space, you have all the required functions. Say you have this part as the linear functions, and say you have a part which are quadratic functions. Fine. So that would be something like this. This is your linear part, and then you have this quadratic part. Fine. Now let us try to analyze what these see. Whatever we do in any signal processing or any other application is just work in these functions. We don't work in any other. We just usually work only in these functions, only in these domains. Linear and quadratic forms. So let us have a clear analysis of these linear and quadratic forms in this. So the linear form first. How did we? So linear form actually came from, if it was one variable, it is y is equal to ax. Fine. This is the linear form in one variable. Fine. Now, if we have multiple variables, how would the linear form look like?
Some linear combination of x and
so it will be y is equal to a1 x1 plus a2 x2 plus so on up to an xn. Okay. So people then started now the motivation here is we want something like this rather than what we have in linear form, what we have in multidimensional case, which is a1 x1 plus a2 x2 plus so on up to an xn. We wanted something like this. So we then started making something called vectors. Okay, and that is a is equal to a1, a2, so on up to an, and then x is equal to x1, x2, so on up to xn. Fine. So we wanted something like these. We created something like this because we wanted to have something in this form. So then we started saying y is equal to A transpose x by defining something called the transpose operation. As if A is equal to A1, A2, so on up to An, then A transpose is A1, A2, so on up to An. Fine, we started defining this. Okay. Then similarly we had the dot product or the inner product. which usually some people denote in this way, which we said A transpose X, and this is a scalar. And then we said y is equal to A transpose X is in a very similar form as seen in the one dimensional case. Do you get that?
Yeah.
One dimensional case, n dimensional case. So in reality, there is nothing like these vectors and all. In reality, these vectors and all that were created for the sake of simplicity. What does that mean? We wanted to see everything in the original way we were used to. That is the y is equal to ax way.
Yeah.
Fine. We wanted to see everything the y is equal to ax way. So we defined something called
Vectors.
Yeah. Find these vectors. Fine. Now that was the way with vectors. Now if you come to quadratic forms of functions, how do we usually have a quadratic form? Y is equal to, if it is x of x1, x2, so on up to xn, we have the quadratic form as x1 square plus x2 square plus so on up to xn square, and there would be some, it would be a1 x1 square plus a2 x2 square plus so on up to an xn square plus b1 x1 x2 plus b2 x2 x3 plus so on up to bn xn x1, where these are all possible combinations. These are nc2 of them, nc2 minus n of them, because n of them have already been included here. So nc2 minus n of them. Fine. All possible omission. So this is your quadratic form. Do you agree with that?
Yes.
Quadratic form. And then you can also have these. After this, you will also have expressions like plus a1 x not a1, say c1 x1 plus c2 x2 plus so on up to cn xn plus d0. Fine. So this is the entire quadratic form. So let us write this again. But this is not homogeneous. Do you see that? Because there are these x1, x2, so let us just try to simplify the homogeneous quadratic form. Let us try to see more about this homogeneous quadratic form, and that is this part. Right? This is your homogeneous quadratic form. Okay, so let us try to have a greater look about this. That will be f of x is f of x1 x2 so on up to xn is equal to a1 x1 square plus a2 x2 square plus so on up to an xn square plus some constant b1 x1 x2 plus so on up to some constant bk xn x1. Fine. Now if I want to represent this, can I represent it this way? 2 sigmas where I varies from 1 to small n, j also varies from 1 to small n. Some say some aij times xi xj. Do you see this? You have all possible combinations. What does this imply? This implies that you first have sigma j is equal to 1 to n, that means j is constant here. Then you have a 1j x1 xj plus a 2j x2 xj plus so on up to a nj xj a nj xn xj.
Xn, Xj, yeah.
Fine. Now
Depending upon
yes.
shape.
Yeah. Now for each of them, what do you have? Now let us have this. Okay. So it is sigma j is equal to 1 to n this one, right? Now this is equivalent to what? Each of them expanded, which is the sum expanded on each, sigma 1 to n a1j x1 xj plus sigma j from 1 to n a2j x2 xj plus so on up to sigma j is equal to 1 to n a nj xn xj. Fine. Now what do we have here? In each of them you have a1, this is a11 x1 squared plus a12 x1 x2 plus so on up to a1 a1n x1 xn. Fine. Then this is for the first one. That means xn. So the first one is this. Then say you have the second one, which is this. So that will be a21 x1 x a21 x2 x1, fine, plus a22 x2 squared plus so on up to a2n x2 xn.
Yeah.
This is the second one. Do you see that? And so on. So this will have all possible this will have all NC2 numbers in total. In total NC2 terms. This expression. This goes on. The last one, if we want to write for clarity, you can write an1 xn x1 plus an2 xn x2 plus so on up to ann xn squared. So this is the last one. So in effect we can write the quadratic form in this way.
Yeah.
That is y is equal to sigma aij xi xj, 2 sigmas, I from 1 to n, j from 1 to n. Fine. Do you see this? Now let me do a small change here. That is not a change. Let me try to emphasize something from this. Let me give something like this: 1 to n xj sigma I from 1 to n aij. Can I do this? Because this summation only depends on j. This xj is only dependent on j. I'll get this j out. Okay. Now let us try to observe what this is. In effect here, let us try to plug aij as bi, because this is for this summation, this is not depending on not depending on j. Since for in this summation this aij no more depends on j, for if you just see it locally, let us take it as bi. Okay. Now this will be sigma j as 1 to n xj sigma I from 1 to n bi xi. Fine.
Yeah.
Now what would this be? Sigma j is equal sigma I is equal to 1 to n bi xi. This is b1 x1 plus b2 x2 plus so on up to bn xn. Which form is this? The linear form.
This is B transpose X.
The linear form. So that is some b transpose x if we take b as b1 b2 so on up to bn. But then we said this b1 b2 bn were aij.
Yeah.
So this will be, this b will be a1 this b will be a1j a2j so on up to anj. Fine, that will be this b. So let us just have it in the back of our mind that this b is this from this. Fine, now that is okay. Let us come back to this expression. Now what you want to do is, to each of this constant you want to multiply. Now this is a constant, isn't it? Constant which only depends on j, right? This is a constant depending on j. Okay, not constant, this depends only on j, not on I, only on j. Fine, so we call this, say, some cj. Cj is this. Fine.
Okay.
Now
Okay.
if you take that, so let us substitute that here. Sigma I is equal to 1 to n j is equal to 1 to n xj cj. Fine, xj cj.
Yes.
Now if I want to write it the earlier way, let me write it this way. I want to write it x transpose c, where x is x1 x2 so on up to xn and c is c1 c2 so on up to cn. Fine.
Okay.
And each of c was defined in this way. So each of cj was actually what in terms of j? Cj is sigma I from 1 to n bi xi, which is sigma I from 1 to n aij xi. You see this j here now. This j is what is being shown here. Okay, so now this is how I wrote this. Fine, x transpose c. Now let me write it this way. So let us expand this. So that will be x transpose is x1 x2 so on up to xn. And this c is c1 c2 so on up to cn. Right. Now we have this cj as each of this c as what? B transpose x. So let us replace this here. So this will be x1 x2 so on up to xn. This will be b1 transpose x, b2 transpose x so on up to bn transpose x, because we took this as this cj as b transpose x. Okay, that was just b transpose x, sorry. Yeah, it was actually this one. Okay, so let me not write it as b, because let me not write it as b anymore. Let me write this as ai. This, let me write it in this format. What is that? aij. So here we have so okay, let us call this bj from now. Let us call this bj. Fine. So here it is. Here it is bj. Let us take this notation as bj. A1j, A2j, Anj. This as bj. So let us. So then this is fine. This will be B1 transpose B2 transpose X, Bn transpose X. Fine. Now, now if I want to do something here, what I want to do is I want to write this as x1, x2, so on up to xn, and this as B1 transpose, B2 transpose, B3 transpose, so on up to Bn transpose into x, which is x1, x2. Do you get this? This earlier expression. Now, what will this be? x1, x2, so on up to xn. Now this B1 transpose is actually just substituting 1 instead of j here. So that will be A11, A21. So this will be A11, A21, A31, so on up to AN1. I am writing the indices not in a proper way here because I haven't taken them in a proper way here. I should have taken J1 instead of 1J, but that's okay. You understand the idea. The second one you have A21, A12, A22, A32 and so on up to AN2, and this goes on up to just by substituting this B transposes here. That is A1N, A2N, so on up to ANN. This is x1, x2, xn. Okay. Now we have x is equal to x1, x2, so on up to xn. This capital A is whatever that Aij matrix was. And then we have this quadratic form as the famous form x transpose Ax.
Nice.
Okay. So this is how we motivated
quadratic form
ourselves for the quadratic
form.
Okay. Now fine. Now let us see something else. Now let us see this for the R2 case. We develop intuition in the R2 case and we generalize to Rn. Intuition in R2 and we generalize to Rn. Okay, so let us see in the R2 case what is the homogeneous equation, which is ax square plus by square plus some 2cxy or cxy. Let us write it 2cxy. Okay, now this, if you want to write it, you could also write some cxy. I am writing it 2cxy. Okay, if you want to write it in this form, it will be x y a b c c xy. Okay, you can multiply this and check. Let us do that. X y a b c c x y. This is x y times ax plus cy. This is cx plus by. Now this is ax squared plus cy ax squared plus cxy plus cxy plus by squared, which is ax squared plus 2by squared plus 2cxy. Fine. Now, so our function, our quadratic, basic quadratic that we have, a homogeneous quadratic, that is, it is at the origin. At the origin. centered at the origin. Centered at the origin. This is equivalently written as xy ab cc xy. Okay. Now let us in specific take our what you call. Okay, this is z. Okay, because I am using y here. This is z. So this is not y. This is z. Fine. Now if I want to draw this, this z with respect to xy, that would be some surface.
Yeah.
Do you see that? Some surface this way or some other way. It would be passing through the origin, because z is equal to 0 at x is equal to xy is equal to 0 is being satisfied. Okay, do you see this?
Yes.
Fine. Now if I want to do something more than this, now if I want to examine some few things from this. Okay, you see, it may pass through the origin or it may not pass through the origin. There are reasons why that happens. So let us say in general it is this. It could be this, okay, or it could be this. Okay, it could be any of these. Now the next thing is I want to see whether I want to check if this function is always above the xy plane.
Okay.
We want to check if this function is always above the xy plane. Okay, so what should I have for that? For this function z is equal to xy ab cc. If this function has to be always above the xy plane, what should happen? Z should be greater than 0 for all x comma y, isn't it?
Yes.
Z should be greater than 0 for all x comma y, except
Right.
x comma y is equal to 0, because at 0 it is obviously 0.
Yeah.
For this for xy not equal to 0, it should always be above this. Okay, so it will pass through the origin, but for every other it will be above. Fine. This is clear. So I want this to be satisfied. So so graphically how could that be? If this was your xyz, if your function is somewhere here where this is okay, some positive quantity.
Okay.
This is one possible quadratic form.
Okay.
Say some c. Okay, then there will be an additional c here. Don't bother that now. So do you get this?
Yes.
This should be, so what should I have is x, y, a, c, b, c, x, y should always be greater than 0 for x comma y not equal to 0. Right? Now,
Right.
let us say in the Rn case, in the Rn case, say this was your Rn. Let us assume, let us just draw only two axes and say this was your Rn. Okay, and then the n plus 1th dimension is this. This is the n plus 1th dimension. Suppose in that world, in that space where this is n plus 1 dimension, I am drawing that curve. And I want this curve to be above Rn space. You are getting that? Above Rn plane in the n plus 1 dimension space.
Okay.
Fine. Because Rn is a plane in that n plus 1 dimension space, or a hyperplane.
Yeah.
Rn is the hyperplane. We call hyperplane.
Definition of hyperplane.
Hyperplane is just a plane in a n dimensional space. If it is 3-dimensional space, we'll call it a plane. And if it is n dimensional space and there is a plane in n dimensional space, then it is called hyperplane. Okay. Rn above Rn, which is a hyperplane in n plus 1 dimension space. Okay, in n plus 1 dimension space, Rn is a, see, in 3-dimensional space, the 2-dimensional space is a subspace, which is a plane in 3-dimensional space. Do you see that? See, if this is your 3-dimensional space, if you take the xy plane, which is an R2 plane,
Yes.
which is a subspace of this 3-dimensional space,
Yes.
which is inside this,
Yes.
same thing. Rn is a hyperplane in n plus 1 dimensional space. Okay, now above this hyperplane, you want to have this curve all above this hyperplane. Okay, so that will be given by this expression. What is this expression? X transpose Ax. Fine. This curve, that is this quadratic curve. Okay, this quadratic form. We are only talking about quadratic curves. Quadratic curve in Rn. This quadratic curve defined in Rn in the n plus 1 dimension space. Okay, this quadratic curve in Rn plus 1, actually drawn in Rn plus 1. Curve drawn. Drawn in Rn plus 1. You want this to be above. So what is that definition? That is X transpose Ax must be greater than 0.
Yeah.
For x not equivalent to 0 in vector form. In vector form or matrix notation.
Yep.
Okay, so and for this should be for all x, belonging to Rn, right?
Yeah.
Now this condition is called the positive definiteness. Okay, so the definition of positive definiteness is a matrix A is called to be positive definite if X transpose Ax is greater than 0 for all x belonging to Rn, and this A belong to say Rn cross n, for all x belonging to Rn except the 0 vector. Fine. So we finally defined something called positive definite matrices. Okay, fine.
Okay.
Now we know that every matrix can be decomposed as a sum of what? Symmetric and asymmetric matrices. How is that? We have A is equal to x plus y. Say x is a symmetric matrix and y is an asymmetric matrix. Fine. Then you have not asymmetric, sorry, skew symmetric. Fine.
Okay. Meaning it's not symmetric.
No. Skew symmetric means y is equal to minus y transpose. Symmetric means x is equal to x transpose.
Okay.
Okay. Now I'll have A transpose is equal to x transpose plus y transpose.
Yeah.
Now if I use these two here, this x transpose is the same as x and this y transpose is equal to minus y.
Yeah.
From these,
Yeah. Right.
these put from these putting into this we get this. So we have two expressions now, which are A is equal to x plus y and A transpose is equal to x minus y.
Yep.
These two, this and this.
Yep.
Now solving you get x is equal to A plus A transpose by 2 and y is equal to A minus A transpose by 2.
Okay.
So this is possible. What we have proved is it is possible for a matrix to be represented as a sum of symmetric and skew symmetric matrices. Fine. Do you get this?
Yeah.
We have proved this. Because you can observe that this is a symmetric matrix and this is an asymmetric matrix. The one you got x is a symmetric matrix and the one y you got is a skew symmetric matrix. Okay. So now let us have this quadratic form saying x transpose bx. Okay, say B is any matrix. Now let B be represented as C plus D, where C is symmetric and D is skew symmetric. Fine. So we'll have x transpose C plus dx, which is x transpose Cx plus x transpose dx. Fine. Now here we have this B belong to R n cross n and x belong to Rn. So are C and D, they belong to R n cross n. Fine. Now, now what I want to tell is, now since we have this x transpose Cx plus x transpose dx. Now each of this is a scalar, right?
Yeah.
Now let us take x transpose dx. D is skew symmetric, right?
Yeah.
D is skew symmetric. Now since this is a scalar, x transpose dx is equal to x transpose dx transpose,
Yeah.
which is x transpose d transpose x, which is minus x transpose dx, because d transpose is equal to minus d
Yep.
because of skew symmetricity. Now what does this imply? X transpose dx is equal to minus x transpose dx, which is x transpose dx is equal to 0. Fine. So for some x transpose bx, you decompose as x transpose cx plus x transpose dx. This becomes 0. So this effectively becomes only the symmetric matrix in place. If you just take the symmetric part of this B matrix, the quadratic form remains. Fine. You just have to take C is equal to B plus B transpose by 2 whenever you have these. Okay, so whenever you have X transpose AX is greater than 0, there is always a skew symmetric term in A which becomes 0. Symmetric part in A which becomes 0. So we only need to analyze the symmetric part of a matrix while doing positive definiteness, while working with positive definiteness or quadratic forms. Did you understand? Positive definiteness.
In X transpose BX. So this means that any quadratic form, the X transpose BX, the B matrix, that's symmetric.
What?
In any quadratic form X transpose BX, the B matrix is symmetric.
Yeah, we can take the symmetric part of B, so we can always consider B is symmetric.
Okay.
Are you getting? You can effectively take the positive form. You can effectively take the symmetric part. Okay.
I mean, that is B is symmetric. I mean, since there is no skew symmetric part, so we can say that X transpose BX, the B matrix, is essentially symmetric.
Yeah, essentially symmetric. That's what. It is actually that you can take this symmetric part of B. So what you do? Theoretically, you only take symmetric matrices in these terms, X transpose. Okay. Theoretically, you only take symmetric. That's what I did here.
Okay, so that's why in optimization problem each and every.
Yeah. That is the reason. Okay, so we'll stop this session now.